Hello, everyone, and welcome to this Mobile World Live webinar as part of our Unwrapped digital series. I'm Kavit Majithia, Senior Editor of Mobile World Live, and I'm delighted to be your moderator for today's event. Over the next hour or so, we are going to be exploring the topic of delivering 5G from high-altitude platforms in the stratosphere, and specifically looking into the work being done by BT, Stratospheric Platforms Ltd, and Cambridge consultants to develop a secure 5G HAPS demonstration system. Now, this really is a hot topic in the industry. And aside from delivering widescale 5G from the stratosphere at a fraction of the cost and the environmental impact of terrestrial, we will also examine additional use cases of this approach. Delighted to say I'm joined by 4 speakers today. Firstly, we have John Wakeling, Research and Network Strategy at BT. Second, we have Neil Unit Jones, Commercial VP at Stratospheric Platforms Ltd. Thirdly, we have Gary Kemp, Program Director at Cambridge Consultants. And last but not least, we have Tim Hatt, Head of Research and Consulting at GSMA Intelligence. Now, while our speakers are presenting, I'd like to encourage our audience to interact by posting comments and questions. We'll have time at the end of the presentation to address some of these questions. Submit a question in the box underneath the slides, and we will try to answer it. And with that, we will kick off with Tim for an overview of the market.
Thank you very much, Kevin, and great to be here. So yeah, we're going to give a brief overview of the HAPS area and what we think are the key trends to sort of set this in the context of the non-terrestrial movement, which has really gained pace. And I think it's going to be a really interesting discussion. So if we can go to the next slide, please. I think it's first important to just contextualize where high altitude platforms sit relative to satellite constellations, and indeed sort of relative to the ground. So what we're showing on this diagram is you can see that a commercial aircraft flies at about 10 kilometers above sea level. HAPS is about double that, around 20. And you can see that that's considerably lower to the ground than any satellite constellation, whether it's low Earth orbit, LEO, MEO, or of course GEO. And the significance of that is that you have a lower latency and ability to deliver higher throughputs. And that's really interesting because it allows for faster speeds on the ground, particularly where you are dealing in rural areas or sometimes semi-rural areas. And so there's a lot of interest in being able to take advantage of the physics of that deployment. We can go to the next slide, please. I think it's important to first outline the rationale for why there is such interest here. And I think there's multiple points here. When we look at the consumer side of things, the coverage gap is still a challenge. And by the coverage gap, we mean the share of the global population or regional population that sits outside the range of a mobile network, be that a 2G, 3G, 4G, or a 5G. And right now, worldwide, that's sort of 500 to 600 million people. But the challenge is that even though we have network coverage over 90% of population, getting that to the final frontier is very challenging economically. And so you can see this table is showing even in 2 years' time, that coverage gap is still, almost 8% of the population. Now, while that is the highest share of population in developing regions like Africa, it's still a challenge in higher income regions like Europe, places like the UK, Germany, even the US. And so, the HAPS rationale really is a global one. And we see a lot of activity to reflect that. Next slide, please. Just to dig in a little bit more to the rural economics point that I made, if you look at what we're showing here is sort of our modeling to show the components of laying network infrastructure in rural areas compared to urban. And you get this sort of headline figure of it being roughly 35% more in terms of the CapEx and OpEx pound for pound. Backhaul links account for the majority of that. It's very expensive, obviously prohibitively expensive in many cases to lay fiber, but even other forms of backhaul like microwave can get very expensive. And so again, this points to the economic advantages of using an aerial constellation like HAPS to be able to service network coverage in areas where it's just not economically feasible to do so from terrestrial. If we can go to the next slide. Thank you. And so given all of that, where do we go? And there's this few points to make here. So what this is showing is actually global take up of mobile subscribers and mobile internet. And you can see those two numbers sort of flattening out, those lines, the red line and the teal line there. And whilst internet penetration worldwide is around sort of 60%, the point I want to make from this slide is if you look at that kind of dotted green line, that's the change in the number of people we're adding to the internet every year. In the past, that was rising by sort of 200, 250 million a year. But you can see the projections are that coming down. And so we're adding people at a much slower rate than was possible. And a large part of that is reflected in the coverage economics. So the HAPS rationale and the broader NTN really plays to this coverage. As standards get in place, the devices become more compatible with it. And as prices, come down as a share of income, the take up is much more interesting than it has been in the past. So there's a huge amount of innovation going on and performance gains in HAPS to help this movement. And we think it's really interesting to follow. So if we can go to the next slide, that is us at GSMA Intelligence. I am now going to pass it over to our next speaker, John from BT. Thank you very much.
Great. Thank you very much, Tim. Good morning, everybody. I'm going to talk to you about some of the technology infrastructure challenges faced in general by telcos and MNOs, using the UK as an exemplar, but you can certainly see that we will be covering issues that are common to most developed economies, just discussed by Tim. So I'm going to talk about that in two contexts, a little bit additional on fixed broadband in the UK, mobile coverage, and including understanding how things like the UK's proposal for a shared rural network will impact on future coverage. I'll come back to speak to satellite in terms of the role that satellite has to play in addressing some of these challenges, and I'll revisit some of the points made earlier on by Tim, speak about those in a bit more detail, and introduce another couple of challenges that we see as well. I'll speak to some of the HAPS platforms that are currently in development, although they've actually been in development for probably well over 25 years. That's how long I've been tracking the technology. And it's interesting to see how things have changed over that time period. And then as an intro into what you're going to hear from partners SPL and CCL, talk about the next steps from BT's perspective. So if I can have the next slide, please. Fixed broadband is what I'm looking at the moment. The interesting thing, even for the UK, which actually has some quite widely varying geography types, is the fact that coverage across those different geographies in terms of premises passed is reasonably consistent across most of the geographies. And in terms of the availability of service, so the terrestrial network build out is reasonably good because populations tend to cluster around areas where it's easier to actually provide coverage. Although obviously in some of the more extreme geography types, you do see the higher speeds in particular start to fall away in terms of coverage. So we need solutions. As Tim's already shown, the cost per build out of terrestrial technology can be extremely challenging. And it's not just costs, there's a lot of logistical challenges in there as well. And the fact that once you've deployed infrastructure to areas of relatively low customer density, you've then got a fixed infrastructure investment, which you then need to monetize and exploit over time. So if we can have the next slide, please, I'll move on to the mobile domain. Here we can see again information from Ofcom, as was the last slide. In fact, a view of coverage today on the left-hand side of the screen, where you have coverage by at least one of the mobile operators up to 4G coverage from all four operators. And there are plans in place looking at how we can create some shared infrastructure for all operators to start reaching out into that final coverage area to provide customer service in additional areas and also provide the potential to support new use cases around such things as connected vehicles, some IoT applications, logistics management, and so forth. But even after the deployment of shared rural network, and the right-hand side is sort of the forecast coverage of the SRN, you still find reasonable coverage gaps where you certainly have fewer operators operating, and the graphic itself is not particularly high resolution, and you will still find in locations where it would appear there should be coverage, you will still find coverage black spots. And quite a few of these, interestingly, can occur around metropolitan areas, purely driven by the geography, shadowing of roads, and so forth. So even with the best endeavors of terrestrial network deployment, we are still going to be finding coverage gaps in rural and some suburban and donut areas around built up areas. So there is still a challenge after we've built out that terrestrial infrastructure. Can I have the next slide, please? Now, satellite. Satellite has a role to play in all of this, and it's not a case of either or between satellite and HAPS, because of course it depends on that last point I just made about the efficiency of your investment in terms of the provision of that new infrastructure and the utilization of the capacity that is provided. So we are looking at HAPS in the context of the available geostationary and low Earth orbit satellite capabilities. And satellite does struggle in one respect, at least with the systems that are being deployed today and foreseeable future, around capacity density. Because if you're trying to pick up remote hamlets, for example, in rural areas, you may find that you can have upwards of 20, 30 premises. They're all trying to gain access to super fast and above broadband speeds. And the fact is that capacity density from satellite beams is fairly sparse. It is certainly useful in the more remote areas where you don't necessarily have such demand density, but it's going to struggle to fulfill all requirements all of the time. The other thing is in terms of being able to access satellite capacity. Now, historically, accessing satellite systems has been pretty much like plugging into a black box. Yes, there is capacity available, but the quality of service is not under the telco or MNO's control. The capacity has been provided on a power bandwidth contract duration basis or data rate contention level and service availability depending on the frequency of operation. So the service provider that owns the customer experience, as it were, doesn't have full control over that control plane from the telco through to the end customer. We do not control the allocation of resources. So the challenge for us is around how can we actually focus where the capacity is needed? How can we manage the quality of experience for the end user where they have specific application requirements? So we're really interested in the evolution of standards which will enable us to do that under 5G, but it still remains a case of will the management plane be extended from the satellite or HAPS capacity provider into our domain so as we can press those buttons, pull those levers to manage our customers' own experience. Next slide, please. In terms of where we're going next, we're in the process of going through some technology evaluation in terms of the component technologies of HAPS payloads. And the picture you can see there is at Astral Park. We currently have some components of a HAPS antenna at Astral Park, where we're doing trials and validations of that underlying technology. And in terms of making sure it does on what it says on the tin, understanding the cost structure of what it takes to bring that capability to market, and how we can actually integrate it into our fixed terrestrial infrastructure. Next year, we'll be looking at working with partners on a use case demonstration, flying that technology on a conventional aircraft, so as we can demonstrate the use cases with a certain level of technology realization in the aircraft, connecting to the ground network, enabling us to control the end user experience. And then, of course, based on the learning from those two activities, we're going to be working through the business case evaluation. And this again is where we're doing the compare and contrast with satellite platforms and indeed other high altitude platform systems that are aiming to provide the same or a similar capability. So we're learning as we go along here. This is pretty much a sequential process for us. We have to check off validation of key principles along the way that would enable us to understand how we could best economically deploy the capability once it becomes available. Next slide, please. We have been looking at HAPS platforms development over the last 25 years. Here you can see the wide range of technology types that have been deployed. So aircraft, hydrogen powered, solar powered, an interesting variety of dirigible structures, all of which have their own pros and cons and abilities in terms of the ability to carry payloads, the ability to generate power, the ability to stay over a particular geographic region for a period of time that's commensurate with the use case that the service provider wishes to execute. And a key thing around this is understanding what the economic profiles are of these systems, because to some extent, from a service provider perspective, we don't care how long each individual platform actually stays up in the sky, because the business model for us is the ability to consume capacity over a geography at a cost per customer per megabit delivered. So that at the end of the day is our primary metric in terms of understanding all the different aspects of each individual system and how it manifests in terms of the service that's provided and the price we're going to pay. If you can just do the next click, please. There's been some big players that have been active in high altitude platforms for a number of years, again, using a variety of technologies and testing the economics of those. But it's really interesting of those big players that they are not progressing with those technologies that they originally chose. So again, that provides some insight as to the economics of which technologies can work at which latitudes, can support which services, and can actually provide an economic operational cost per unit capacity or customer that's being delivered to the end user. So a lot of lessons being learned. And as I said, this technology has been in development for about the last 25 years since the original proposals around Sky Station and Angel Technologies. There is still learning to be done for us in terms of understanding what each system type is capable of, but we're keen to work with partners to develop that underlying technology, doing the trials of service integration to enable us to make an informed choice about how and where HAPS can play a role. And if you could give the final slide, please. Thank you.
Right, thank you, John. It's Neil here from Stratospheric Platforms, and picking up from John's last point about the wide and varied number of HAPS that are available, I'd like to talk to you about the Stratomast, which is our rigid aircraft, hydrogen-powered rigid aircraft. Next slide, please, Anna. So the use case for this, or the particular use case that the thing was designed for, is 5G connectivity from the stratosphere. So think of this, it's really helpful to think of this as a 20-kilometer high cell phone tower or mobile phone mast. That's everything else in your brain can be entirely equivalent to that. The only difference, of course, is that we need an aircraft to deliver that, because you can't make a steel tower 20 kilometers high. The effect of broadcasting from above or relaying from above the signal is that there's no interference from trees and buildings and shadowing. So we have modeled the fact that the experience for the user will be equivalent to being 300 meters away from a terrestrial tower, which is therefore going to provide high speed to every user over a large area. And the picture you can see there is a model of how the beams are created on the ground, because each aircraft can create up to 450, 500 individual beams that act in a similar way to cellular cells today. Next slide, please, Hannah. So my session here is really to talk about the anatomy of an aircraft and what we're doing to actually provide that aircraft that can be used for telecom quality of service. And by that I mean the aircraft needs to stay as still as a mobile phone mast would be, right? It can't exactly because it needs to fly, but it will station hold 99.99% of the time so that you know that you can get service. And the way that we do that is through having a high power availability. And that gives us two things. Firstly, the ability to drive into stratospheric wind. So 99.99% of the time, the aircraft will not be affected by wind and will be able to stay in exactly the right position to provide service to users. But also the hydrogen power gives a huge amount of power to a payload. So we can have a large payload, 140 kilos, with 22 kilowatts of free power, which will give telco quality service from that very high tower. And finally, any aircraft will need to cover off aircraft things, right? That's why I'm here. I'm an aircraft guy, and therefore, and it must be certified for flight. It must be able to be a proper aircraft that operates in amongst other aircraft. It cannot be an exotic device that can only work under special circumstances. Next slide, please, Hannah. In order to get an aircraft like that, there's a few companies in the world who are able to design one of these, and we went to Scaled Composites in California and gave them the design brief, which is called a TLAR, a top level aircraft design brief, which says what we needed the aircraft to do. And we came up with, or they came up with 17 different designs: blended wing, two bodies, two fuselage, different sorts of empennage, tailplane, different sorts of materials. And of those 17 designs came up with the V-tail long wing design that you've just seen, that I'll talk a little bit more about in a second. During that design process, one of the key attributes was not, in fact, as John has already pointed out, was not how long can this thing stay in the sky. It needs to stay up there for a reasonable amount of time, because the turnaround time is essentially dead, and therefore that's wasted time that your aircraft is not providing service. But actually, that asymptotically fades away after about 7 to 10 days. So actually, what we really want is a plane that can stay still, an aircraft that can stay still. So in the parametric and sensitivity analysis that we did, where you've got two factors, maybe the length of the wing divided by the mass of the aircraft, for example, that may have a play on how the aircraft performs and whether it can station hold. And you would choose a place on that graph to make sure that if one of those varied a little bit, like the mass, because maybe we add a new box, or maybe we take a box off, or we add a different sort of aircraft control system, that it wouldn't massively affect the other parameter. So a lot of that went into play, and that's what drives the design of these aircraft is how does varying one thing vary another thing. And we want it to be repeatable. We need to be able to make a lot of these things, because ultimately, to provide service over a large area, you're going to need a lot of aircraft. So the upshot was a very fantastic design of an aircraft that we're about to start building now. Next slide, please, Hannah. Certification is vitally important for anything that flies, and it's because of safety, and it's because of all us human beings who need to be safe from aircraft and in aircraft. Although this is a pilotless aircraft, it has no crew. And so one of the very first conversations ever had in this company, probably the second one to is it worth doing, was let's phone EASA, the European regulator, to make sure that what we design right from the start is going to be capable of flight in civil airspace. Because nobody's going to want to operate an aircraft that can only take off from limited places in the world, or that has to ascend or descend through a segregated bit of airspace, which is very difficult to achieve, particularly when you're entering a market that doesn't exist, to try and get authorities and other airlines, etc., to avoid a piece of the sky. So we knew we needed to be in a place where we didn't have to avoid a piece of the sky. And to do that, we enter into discussions with the EASA. And one example of that is there's a wing section. That's a 10-meter section of wing. The entire wingspan of the aircraft is 56 meters. So imagine 5 of those stacked next to each other. You can see the picture of a person at the end there. And that was tested for load and stress and was successful. And that's just an example of the way that we're making sure that this aircraft is capable of flying integrated with the rest of airspace. Okay, Hannah. So a little bit of anatomy. The one that everybody wants to know about, happy to take questions at the end, is hydrogen. What is it about hydrogen? It's the energy density. I guess I'm talking to a lot of telecoms people here, but if you were a lot of aerospace people, you already know that hydrogen is the future fuel of choice for flight. In our case, liquid hydrogen stored in those 2 large tanks you can see in the center, the green balls there. They are 3.5 meter diameter tanks. And that hydrogen provides power to the engines, where we are not using fuel cells, which is the other question we get a lot. We are burning hydrogen directly. Obviously, when you burn hydrogen, you just get water and forward power. And so that power allows us to station hold the aircraft. Long wing gives a low drag. There's nothing universal about this design. If you think of very, very high altitude aircraft, like generally it's the spy plane kind of thing you can imagine. A U-2 has got a very long, thin wing. It's exactly the same theory. The antenna is a large 3x3 meter antenna. It's a phased array antenna that Gary will talk a bit more about later on. And that is housed in the front of the aircraft. And it has, the reason why we have an overwing is that the antenna has a full view of the earth below, so that we get full service. We have, for the backhaul, which is how we then connect all the signals back to the ground, we use a millimeter wave, and this is analogous to essentially to the fiber that would run to the base of a tower and up the tower. This is how we get back into the core network. And a bunch of aerospace stuff. Okay, so beyond visual line of sight, there's new technologies springing into being all the time, particularly in remotely piloted or autonomous vehicles, is that they have to be able to work when no one can see them, beyond visual line of sight. And that requires data link, which also requires our friends in the satellite world, GPS, collision avoidance, landing systems, all the aerospace things that you would expect to have in an aircraft can all be housed in this vehicle. And that's what's being designed, and that's what we're going to build. I'm going to move on now to a video that describes how this thing will work, and how it works is called ConOps, Concept of Operations. So this shows how the aircraft, this is a scale, you can see how big it is compared to an airport, and how it ascends through controlled airspace. These are blocks of controlled airspace, and this is real data. All the white dots you can see there are real-time data from what happened over UK airspace a couple of years ago. And the aircraft will ascend through those regular air traffic up to the stratosphere, where it then flies above all other traffic and synchronizes with a partner aircraft that it's about to replace. So you can see the green aircraft is the incoming, the purple aircraft is going to leave. We swap over from one to the other to maintain service. What we're showing here is they're flying in 10-kilometer circle diameters at flight level 600, 60,000 feet, 20,000 meters. And here in this example, we're showing 2 aircraft flying in formation, which gives you greater data density, but it will work just as well with 1. Back again, there's London. This is a very busy day flying over London, like every busy day. You can see Heathrow for those that know it. And this shows how the HAPS, not to scale, will station hold above all other traffic and provide coverage through that traffic and to the ground below. So in an example here, the United Kingdom, because that's where we are, could be covered by, in this case, a lot of HAPS for data density, but about 24 of these. For those that know, think of Yorkshire. 1 HAP can cover the area of Yorkshire, and they will provide 24/7 coverage throughout the land to provide the white spot that John spoke about, with about 60 airport movements a day. So, a couple of times an hour, 3 times an hour, an aircraft would depart and dispatch, and that is in amongst regular air traffic. Okay, Hannah, we can move on. Hydrogen, very interesting. This is Prestwick Airport, a view from Google Earth, credit to Google. Prestwick Airport is a great example of where we could operate this aircraft. In fact, we could operate from pretty much every airport in the UK if we wanted to, or around the world. Prestwick is a great place because it's windy, and that you could quite easily build a wind farm off the coast, subject to the licensing, which is actually the hard part, and or a solar panel farm in a local field, which you can see the red dot there, and that would provide enough hydrogen to power the fleet that I just showed in the previous video, so that we could have a self-sustaining telco infrastructure built with energy that you don't need to import from anywhere else. Now, just want to imagine that for a second. You could cookie cut that to anywhere on planet Earth. As long as you have sunshine and or wind and or seawater, you can make hydrogen. And of course, sell the extra hydrogen to the grid. So as the hydrogen economy becomes a greater thing, so this aircraft will slot neatly into that. And it has to be said also, as the ESG agenda improves, let's say the word improves in the UK and everywhere else, telecoms infrastructure consumes a large amount of electricity. It's part of what we have in all of our nations. If that electricity can be produced using hydrogen and directly fueling that network, then that's definitely a good thing, right? Next one, please, Hannah. We've done some real world demonstrations. So HAPS exists today, and so do piloted HAPS. So we took an aircraft with a pilot, put a regular 4G, in this case, antenna working with Deutsche Telekom, and flew it over an area in Bavaria. And there were two sort of connections that could be made. One from the HAP, so a regular cell phone, in fact, was attached to the HAP, and also to a terrestrial network in a small town. And if you could look at the right-hand graph first, you can definitely see this. And in your real-world experience, you know this, that as you drive through a small village, for example, your signal will improve as you go near an antenna, and it will fade as you go past it. That's just life, and we'll deal with that in our rural lives. Whereas for the HAP, we had good signal throughout. Of course we did, because the HAP was covering all of those fields that you can see as well. It was covering everything, because that's what HAPs do. So we got some real live empirical evidence to back up the modeling that we'd done. And now I'd just like to just share with you a video of what the future will look like. We had a render created of the aircraft and how it will actually operate. So Hannah, if you could just roll that video, please. Thank you, Hannah. Very quickly want to address one question that came in from the audience. What are the noise pollution and air traffic safety implications from having multiple potential HAPS constellation in operation? Very little. You saw there that the United Kingdom could be covered by 24 aircraft. Think about how many aircraft movements happen in the UK today using jet engines. Hundreds. And so we would be doing 60 movements using aircraft with a silent engine that just spins a rotating prop. But great question. What's next? So right now, John talked about the fact that we're demonstrating the antenna on BT's private core network right now. Go to LinkedIn, you'll find a couple of posts about that. It's very interesting. What we're going to do after that is take the antenna and integrate it onto an aircraft, a Britten Norman Islander, a great workhorse of an aircraft, and do those flight trials that John talked about. If you quickly go to the next slide, please, Hannah. And this is what the next trial is going to be. So we lift it off the ground. It's important that we do that so that we can work out how the beamforming is going to operate. It works well in the model, and it's currently working very well from a tower pointing to the ground. But we want to release it from the ground, if you like, remove it from its umbilical and put it in an aircraft. And the other thing that we want to do is we're talking to partners in the satellite industry, because there's great utility here for working with satellite to use the massive backhaul capability that you've got with a satellite, so that if your aircraft is operating in an area where there is no ground-based infrastructure for a HAP ground station, you can use satellite to do that backhaul. So those are the next trials we're going to do. We're starting those next year, and it all looks very positive. Final slide then, Hannah, is a picture of our fantastic antenna, which is currently on a balcony in Adastral Park. I'd like to hand over to Gary Kemp to talk more about the technology.
Thanks, Neil. Can you see me? Yes, good. Well, good morning, everybody. So I'm Gary from Cambridge Consultants. So you've heard about the challenge. It's how to roll out 5G everywhere and provide a high-level service across a whole country, not just to cities, but the harder to reach areas where it becomes very expensive and takes a lot of time to roll out terrestrial systems. I'm going to talk about Cambridge Consultants' role in developing this the technology to meet this challenge. We've been involved in this program and working with Stratospheric Platforms since 2015. We do development of next generation product systems and services for our clients to create things that are highly ambitious, that have never been done before, and this really does represent the sort of challenge that we love. When you have an aircraft that carries fuel, as Neil mentioned, you can carry a substantial payload, and that enables you to provide the sort of capability that you need to provide a high level of service. Next slide, please. So the engineering challenge is multidimensional, not only in terms of creating a very large all digital phased array antenna system. So all of the RF challenge and the signal processing challenge that goes with that, but also doing that in a form that can be carried by an aircraft, can survive in the stratosphere, can be cooled by a very small amount of atmospheric air, as evidenced by, you can see some of the very long, thin heat sinks lurking underneath the array panel there. And also then survive not just in the stratosphere, but on the way up and down through the lower atmosphere, where the air might be moist and warm, relatively speaking, and keep things from icing up and so on when they arrive at the stratosphere, where it's dry and very cold. So all of that together represents a very stiff challenge, and it brings together many engineering disciplines to achieve it. Next slide, please. So here's a rendering of the full-sized array that is designed for the Stratomast. So it's over 3 meters square. It's got a lot of components. When you've got a very large phased array like this, every element there is a transmit-receive radio with 2 polarizations, individually addressable. So it's every element is individually digitally controlled. When you've got that degree of control and that size, you have a lot of flexibility in how you form beams, This array has 2048 elements. It's constructed as a series of tiles. So each tile is an 8x8 element array, and there are 32 tiles there. Each tile is separately controlled, has its own processor, and talks to its neighbors. So when you build up an array of any size you want from any number of tiles, they communicate with each other and kind of sort themselves out to form one large array, acting as one antenna. When you have such a massive array, you can form many beams. So you can form hundreds of beams simultaneously. You can because it's digital, you can very quickly change the beam pattern on the ground. You can keep the beams fixed in place as the aircraft moves by re-steering constantly. You can cover a very wide area and create a lot of individual independent cells. You can also dynamically change where you put the service in response to demand. And John mentioned how do you put the service where it's needed. By re-steering in software, you can allocate more or less service to the beams that are covering different parts of the ground and respond to demand even at different times of day, you know, when there's day-night commute and that sort of thing. So yes, you've got that degree of flexibility. Next slide, please. So each of the circular patches here, you can see within them are many smaller green patches, and each of the small green patches is a beam. Every beam can be allocated to a cell, or they can be aggregated into a number of cells. The job of the array is to aggregate the signals from all of those individual beams and into as few as possible high bandwidth backhaul channels back down to the ground, and the system becomes very effective by the multiplier of how few stations on the ground you have versus how many frontal beams you can generate. Next slide, please. So this is a small video of that's Brighton on the coast at the bottom there. So you can see that as the aircraft goes around its circuit, we're constantly re-steering the beams to hold them in position as the aircraft rotates. We are also able to control spillover. So along the coast there, you can see we've cut off the service where it's not needed. And that's important, for example, at national boundaries where spillover of interference across boundaries needs to be minimized. Next slide, please. Yes, so here is just another image of the antenna under the fuselage of an airframe, showing that it's a low profile design. It's optimized to be low for all the things that aircraft manufacturers need, which is low size, weight, and power, and for cooling without inducing drag on the airframe. So the more we optimize the antenna in all of those respects, the longer the aircraft can stay aloft on its fuel load. And it has to achieve this cooling in the exceptionally thin air of the stratosphere. So the air pressure is about 1/10 of sea level, which means there's just a breath of air to cool the array. So that's part of the engineering challenge that we're meeting. Next picture, please. Next slide. So again, here's the array that we've built so far. It's sitting in at Astral Park right now, undergoing trials, as John mentioned. This is in our test chamber in Cambridge, UK. It's 4 tiles in a 4x1 arrangement, and that's allowed us to verify a lot of the performance parameters of the array. We've overcome many of the technical challenges already. If we look at the next slide, please. So here are some beam plots. Top plot shows 9 different beams created simultaneously, steered at different azimuth angles. And the lower plot shows that we can control the side lobe levels of the beams by shaping the signals across the array to the individual antenna elements, and we can control how much we're controlling how much spillover we have between cells, and we can optimize for that. Both of these are showing very good agreement with theory, which means that we have high confidence in our modeling of the system, and that gives us confidence in predicting how the array will perform in the field and in deployment, so that we can plan the way that we deploy the system in the air. The next steps in the development are we're currently doing the field trials with BT, and then working towards flight trials on Britten-Norman aircraft as mentioned. And I think that's my last slide. Thank you.
Thank you, guys. Thanks to John and Tim, Gary and Neil for that. That was great. We've got some time now for some questions, and there's still time to ask questions, so please do so if anything comes up. We've got about 15 minutes, so we'll kick off with one for the floor. How resilient are 5G-enabled HAPS platforms to communications jamming and cyber attacks?
I'll take that, thanks. So it's essentially the same as for a cell tower. So this is a radio system, and the resilience to jamming is all about the data that's being carried and how that data is protected in the same way for other cellular systems.
Great. We've got another one here. What's the point of differentiation 5G from HAPS versus 5G NTN satellites?
I can start with that one. I spoke about it in my presentation slot, actually. One of the key things for us is about capacity density. The thing is, with satellites, they tend to have relatively large beams, and because of the power and payload mass constraints on satellite, there's a limit to how much flexibility can be built into the infrastructure. So what we're keen on is the ability to move capacity where we need it, because demand profiles or demand distribution can change over the lifetime of any system. And we're interested in the ability to adapt to hotspots in demand, things like special events, for example, or incidents the blue light services need to respond to. So you need to put a high quality capacity into different areas for short periods of time. So it's around that capacity density and flexibility piece that provides the differentiator in that sense.
Yeah, and just to build on that, I think the signal strength altitude trade-off, which I also mentioned, one of the challenges LEO satellites face, while they have a wider ground area coverage because they're higher in the sky, is to John's point, there just isn't. It's difficult to service very high density cells for that. And sometimes you do see signal degradation, and there's still a challenge about being able to make that more flexible. Whereas HAPS, has a better beat on that because it flies at a lower posture.
That makes sense. Thanks, Tim. I guess this applies to all of you. How does what you have developed translate to new frequency bands?
Yes, the principles apply. Phased array systems. The array that we've developed covers bands 1 and 7 LTE at the moment, all of 2-ish to 2.7-ish gigahertz. But it all scales, the physics all scales. As you get much higher in frequency, the challenge becomes packing density of the electronics. You don't need any less electronics as you go up in frequency, but it all gets kind of packed closer together. So you have to address the packaging and thermal management challenge as you go up much higher in frequency.
Okay. Neil, we've got one here for you. How resilient are HAPS aircrafts to severe weather events? And what happens when a HAPS goes down, literally? Sorry, Neil, I think you're on mute.
Thank you. Somebody else asked about climate change and storms, and somebody else asked about how it would be impacted by ash from volcanics. So I think I can cover all of those off. Firstly, the stratosphere itself is a very benign atmosphere. As Gary said, it's about 1/10. In fact, it's about 6% of the atmosphere down at sea level. And the wind in the stratosphere stays in the same direction pretty much all the time. There's very limited variation, whereas down here we get in the big soup of the atmosphere. At the top of the atmosphere, it doesn't move a lot, so it's very predictable. So we know where we're going to be. Down here though, where we have to fly through, we can diverse. So we don't need to operate from one airport. If there's a big storm happening in Scotland, for example, I talked about Prestwick, we could have another airport. The range of this aircraft is huge. You can fly around the Earth on one tank of hydrogen, right? So we could put it in Munich and still serve the UK. We could put it in anywhere in Brazil and serve, you know, Latin America. So you could get some diversity there. And the thing about what happens when it goes wrong, there's two mitigations here. The aircraft itself is very large. It's 56-meter wingspan, about the same as a Dreamliner or a 787, but it only weighs about the same as a domestic truck. You know, it weighs about 4,000 kilos on takeoff, 2,000 for the aircraft and 1,500 for the fuel. So it's very low weight density. And if it were to hit the ground, it would simply crumple up. And that's if it hit the ground. We would have plenty of opportunity to know that this thing was going to come down, and you divert it to the sea, you divert it to somewhere that's not populated. In the history of aviation, number of human beings killed by falling aircraft is vanishingly small. I think there's been 2 events that have happened in 100 years of aviation. So it actually is a very safe platform from that point of view.
Another one here. When will HAPS be commercially deployed?
Oh, I can do that one as well. They are ready. John showed a great picture profile of lots of different HAPs, and some of those guys, you can phone them today and they will put your payload on a HAP and fly it for you. And there's a great organization, I encourage everybody to go and check it out, called the HAPS Alliance. We're part of it, everybody else. It's one of those kind of markets where we're all sort of competitors, but actually joining together and creating a bit of strength is also good. So there's a trade body. Personally, the stratospheric HAP that we're developing with the hydrogen technology, that'll be commercially available 2026, 27. So let's call it Q4 26. But today you can go buy HAP service. Depends upon what your payload and your power requirement is.
Okay. The phased array opens up some new market opportunities, such as drone detection and control over wide areas. Presumably, the 5G array can also sense positionally to a high accuracy. Positionally, sorry. What other market opportunities are opened by this platform?
I can start on that. So yes, it's a it's a large antenna with a very large receive area and a very high transmit power. So it can be repurposed in a number of ways. So you can reconfigure and have and create a radar that would have very long range and very high sensitivity. You could reconfigure as a for situational awareness type applications as well. So where you want to measure position to very high accuracy.
If I can just pick up on some of the other market opportunities and use cases. So the one we've talked about a lot today is rural connectivity, for example, and fixed wireless access to properties. But actually, if you've got a 22 kilowatt power socket stationary in the sky, who wouldn't want that, right? So for humanitarian requirements, so let's say there's an earthquake, all the mobile phones are buried in rubble. Mobile phones are near the humans. You can use this to go find out where the mobile phones are. It flies above the storm, right? Because it's in the stratosphere. So it can be used for disaster relief, humanitarian stuff, monitoring coastlines, earth sensing, earth observation, pollution monitoring, you name it. If you've got a HAP with a space to put a sensor, you could put anything you want in there.
Okay, we've got about 5 minutes to go, so let's get some more in. Do you foresee HAPS making rural tower sites becoming redundant on a midterm?
John, do you want to have a go?
Yeah, I'm going to speak to that. Not necessarily in the midterm. The thing is that, again, capacity density is all relative. So again, where you could use a high altitude platform or indeed a satellite system to effectively show you where you've got peaks of demand or high density of demand that is growing, it may make a business case viable to deploy terrestrial infrastructure, so as you can then reuse the HAPS capability to provide coverage elsewhere or support other service types. So I don't necessarily see it making rural towers obsolete, but it certainly gives us a lot more flexibility in terms of how, when, where we actually deploy physical infrastructure on the ground to pick up certain aspects of rural demand.
Okay, and one for Gary. Do you require revisions to the 3GPP specifications, or is use of HAPS already allowed in the 5G, 6G standards? Which release will allow this mode? I've lost Gary. Okay, let's move on.
Okay, in which case I'll speak a bit to that.
Yep.
I'm not completely versed in 3GPP, but there may be some things we need to look at. There is already activity in 3GPP looking at non-terrestrial networks in general and some satellite elements in particular. There may be things we need to look at in terms of effectively all users in a HAPS platform are at the edge of coverage of what would be referred to as a big macro cell. So there may be some issues around some of the protocols in that respect. The thing I'm most interested in is, as I said earlier on, the ability of service providers to actually control the quality of experience of the end user whilst they have roamed on to a HAPS platform infrastructure. So we need to look at the provisions in the existing and projected release 18 of 3GPP as to whether they facilitate our ability to do that, and if not, then what else do we need to build into the standard to enable that?
Okay, I think we've got time for maybe 2 more. On a HAPS, in which area could a satellite antenna be installed such that its signal is not attenuated? Are there any weight restrictions on the antenna, and are there any power restrictions?
You're mute, Neil.
I keep doing that. I'll pick that up. Just like a phased array antenna that you might have on the top of a commercial airline, you can put an antenna on top of the aircraft. In fact, we could also put a gimbal and a directional antenna inside the aircraft and get our satellite connectivity that way. The weight restrictions classically with in aerospace, every kilo is less fuel, less or more endurance. So, but no specific weight restrictions. It just reduces the amount of time that you can fly. We think we get an hour per kilo. So for every kilo we can save, we have another hour in the sky. And power restrictions come down to just the fact that you've got 22 kilowatts. When you've used up 22 kilowatts, you've got no more kilowatts. But it's plenty. It's a heck of a power supply, is that.
Okay, guys, I think we've run out of time, sadly. We've had some great questions. Thanks to our speakers today and our audience for taking part. If we didn't answer your question just now, someone from the team will get back to you